So a very good day once again. And trust you can all hear me. Can Gospel or Gaga hear me?
Yes, I can hear you, sir.
Okay, we have one Adewale in class. Can you hear me, please? Okay, hands up. Okay, well, I can't, we can talk right now, okay. Okay, that's fine. So we just get busy. We'll call this information theory and coding revisited. Well, we already gave a description of what we are going to be looking at. So now we just delve into the business of the day. So we say information theory and coding revisited. Okay. So as you already know, information theory actually addresses the problem of information transmission, processing, extraction, and utilization from a pure statistical perspective, okay? Perspective. So if we say that information theory deals with the problem of information transmission, processing, extraction, and utilization from a pure statistical perspective, then it means that the variables that we need to put through the channel, for instance, the communication channel, has to be some random variables. So for instance, if we are given, say, a random variable X as the input to a system, parameterized by some characteristics, and then we get an output variable, random variable Y, such that the output should be a replica of the input, or better still, an estimated value of the input, then we can now describe the relationship between X and Y. And you already know, like we mentioned earlier, that the mutual relationship between X and Y will be the amount of information gained about X from Y. So it means that intuitively, we have an I at this point, Y, and we're trying to observe the system to see what is coming in. And the only thing we know that is coming in all the way is X, but we don't know what is in this system. Now, this system have the capacity to distort, okay? To distort this parameter X, such that the mutual relationship between X and Y will be the amount of information gained about X from Y. So intuitively, the mutual information will be a measure of the amount of information that can be obtained about X from Y. Okay? And now we are looking at two random variables. And here we now say the mutual information is described in this manner. So if this is clear, we now see that since the mutual information describes the relationship between two random variables, X and Y, we now have to deal with some questions. And what are these questions? Now, the first is, at what point, the first question we'll have to deal with, at what point will it either be possible or impossible to observe X from Y? Recall that we have X fed into a system for which we get Y, such that Y is either the same as X or better still an estimated value of X if distorted. So at what point over this communication system will it either be possible or impossible to observe X from Y? Now, should we try to scale down a little, we now have another question to deal with. Now, and that is, what could, this is a question mark. So what could impede the possibility of observing X from Y? And technically, to address these questions, we will have to solve two fundamental problems. And the first problem is going to be data compression problem. And the second is going to be data transmission. This is N, transmission problem. And it will interest you to know that the whole of information theory and coding strives to solve these two problems: data compression problem and data transmission problem. And we already described that the full description of this is the mutual information, okay, between X and Y, because we want to measure or want to be able to tell the amount of information about X we can actually observe from Y, okay? And now, as you will see shortly, the ultimate data compression limit that addresses the data compression problem is the entropy, H. While the ultimate data transmission limit is the same as the channel capacity, C, okay? Channel capacity. And in terms of the mutual information, entropy is the minimum value of the mutual information, while channel capacity is the maximum value of the mutual information. And once we are able to tell this, you will now see that, okay, let's change this color, that we have two extremes. You see this in the videos we already uploaded. So at this limit, we try to deal with the data compression limit, data compression limit. And at this point, we try to deal with data transmission limit. And here, we already said this is the entropy. And here we said this is the channel capacity. And this gives us the minimization of the mutual information, while this gives us the maximization of the mutual information. And technically, as we'll see in information measure, based on what Claude Shannon postulated, we also have reliable transmission, error-free transmission over the communication channel, then this rate, H, should be less than or equal to the capacity of the channel. Okay? So, in other words, the symbol transmission has to be done in such a way that it does not overflow the capacity of the channel. So at some point or in every write, it should be less or equal to the capacity of the channel. So let us wind this. You now see that the data compression, as we already mentioned, the data compression limit may therefore be represented as the minimization of the mutual information, such that the entropy is the same as the minimum value of the mutual information. And also, the data transmission limits may be represented as the maximization of the mutual information such that channel capacity is the same as the maximum value of the mutual information. Now, this gives a broad overview, a general overview of the information theory component of what we intend to study in this course. How about the coding theory? Now, in a similar vein, you'll see from the outline that the coding theory focuses on developing explicit codes known as your either channel codes or source codes, okay? Now, for improving the effectiveness and lowering the error rate of data transmission over the communication channel, okay? Now, we want to anticipate that the channel, an ideal channel, is noisy. Now, how do I mean? Looking at the little architecture I pulled up earlier, let's say this is your live network. We have your 3-band antennas here. Now we have another mass here. We have your sectorized antennas, as we call them. And let's say at this point, we have sectorized antennas here. Okay, here we have band antennas. We have band antennas. So let's assume this is our BSC, okay? Such that through the microwave link, we are able to power these base stations, okay? And now, here, we have buildings of different sizes and materials. We have trees, right? Then we have human beings interacting. We have cars, you know, and all manner of things. Okay, bicycles, you know. Then we have some guys, you know, all over the place. And then the band antenna signals bounce off buildings, okay? And then through multi-part activities, so we now have a chaotic channel, okay? Some are absorbed, some are reflected, and then in the middle of all of this chaotic process or processes, we now have your mobile devices, okay? your personal computers, all of those also interacting, okay? Then your security vehicles with some radio antennas on them, okay? So all manner of activities going on. So you now realize that signals get to you through multipath. So it means that we experience high level of interference in this channel, interference. Okay, so in other words, recall we have either constructive or destructive, right? So it's either the signals add up together and then the strength or the power of that signal amplifies, or the signals cancel out and then we have a zero zone. So that's total loss of signal. And then we now begin to deal with channel fading issues, okay? Then we want to address this problem. So there's every tendency for your mobile device within this channel, like I mentioned earlier, to actually experience signal coverage. But we know that in any communication channel, for instance, that we deal with two major issues: coverage problem and quality problem, right? So we're going to talk about signal quality or signal coverage. Now, the fact that there's coverage does not mean that the quality will be enhanced, okay? So there could be coverage without, with bad quality. So what do? We try to solve this problem. And one of the ways we could solve this problem, now the impact of these quality issues is that we are not able to engage in any reasonable or in any reasonable communication process. Probably you try to engage the internet, you are not able to connect. It keeps loading and loading and loading. Probably you get, you try to initiate a call, it either drops, okay? And then, bad quality, ethno problem could, cause a whole lot. And along the line, you now realize that you are able to communicate, but everything is really crappy. At some point, you send a test file, and then you see it's scattered somehow, more like corrupted, okay? And then we now want to solve one fundamental problem. We want to preserve the integrity of what is being transmitted, okay? And then this brings us back to the signal processing, okay? And don't forget that the entire channel can be modeled as a filter, isn't it? Are you with me? I'd like to hear you talk to me. Is Mr. Ebon still in class?
Yes, I'm with you.
Now, do you believe that the channel itself acts as a filter?
Well, if it is designed to act that way.
No, I'm not saying it's been designed to act that way. I'm trying to say it's a filter.
Okay.
by nature, that the channel itself is a filter.
Okay, okay.
No, I don't want you to just say, okay. Do you believe so? You could have a contrary view.
Well, I think the channel is just to conduct whatever you sent into it.
Okay.
And with the noise and everything, it will carry everything to the destination.
Okay. So now I send X, my input, into this channel, and then I get Y. Is it possible to receive the exact replica of what was transmitted once it goes into a channel?
It's possible.
In practice?
No, it's not possible in practice, but theoretically.
Okay, I mean in practice. So what are we going to receive at this point?
It's going to be distorted.
Okay, so it means
or very close to it, depending on the design.
So it means that we are going to get an estimated value. So we add a hat on it, right?
Yeah. Yes.
Okay. Now, what is the cause of this distortion?
maybe the noise in the environment and all that.
Okay. So that's the channel, right?
Yes.
So it means
From the
the channel filtered your input.
well, if the channel didn't filter the inputs, it means it will mix up. In fact, if the noise and all that is encountering along the channel is much, you may even lose the original information that was sent.
Okay, so now do you believe the channel is a filter?
Yes, we have to do something about that channel if we must have what we sent through it.
So it means the channel is a filter, right?
Yes.
Okay. Okay. Now, if we get that understanding, it means that in digital signal processing, all you now get to do is to design filters.
Okay.
So in communication system, what we try to do is to design filters. Now, why am I interested in the chaotic arrangement within this channel? I know it is chaotic. So many signals. And should we have signals at the same frequency, they will interfere, okay? And in your cellular communication system, we now have to do what we call frequency reuse, right? So we have this cell.
Okay.
Now we have another cell, we have another cell, okay? And let's take your GSM, for instance. We have your 900 megahertz, right? 1800 megahertz. We have 2100 megahertz. So this 3G, right? This 2G.
Okay.
Yeah, this 2G. So then we have 4G. Now for 4G, we move between 400. We try to reuse some of these frequencies, okay? That's the interesting thing. Because now we are moving from WCDMA. Here we are still talking TDMA, right? To OFDM, the multiple access, right? The access technique of the OFDM modulation technique. That's OFDMA. So this is 4G. Now, the bottom line is this. We are doing some spreading here. So we have pilot signal, and we do some spreading of, let's not go there. Now we have TDMA. Here we are talking time slots, right? Okay. And now in your GSM, what is the carrier size? You remember 200 kilohertz, right?
Yeah.
So we have about 8 time slots mapped into this frequency zone. So in other words, you can be paged on a particular channel. I'm just talking your regular GSM whatsoever.
Okay.
Now, of this, in 900, if I'm not making a mistake, you have the uplink and the downlink. So at the end of the day, we have about 25 megahertz bandwidth that can be shared by the operators. And that is why the GSM technology can support only 5 operators. It cannot support more than 5 operators. Because if you do your separation and do your analysis, well, this is not a mobile communication class. I'm just trying to come somewhere. We're trying to do coding, but let's take it from the practical perspective. So here we have 25 megahertz available by your, that's what NCC can spread across. In 1800 megahertz, we have 75 megahertz. So 25 divided by 5, that's 5, right?
Yes.
So it means that each operator is allocated 5 megahertz bandwidth for their GSM operator in 900 megahertz. Now 75 divided by 5 is 15, right? Isn't it? Hope I'm not making a mistake. Yeah, 15. So now you observe that in Nigeria, how many operators do we have? 5 operators, right? Some have sold, they keep reselling.
Okay.
Isn't it? And that is why NCC cannot give new license They can only sell the license of an existing. That's why you see at some point, is it Airtel, Econet? They kept changing and reselling, right?
Yes.
So I know we used to have Globalcom, MTN. I think there's the one owned by Nigeria. Something
Mtel.
yeah, Mtel.
Yes.
I'm sure they are still holding onto their license. Then we have
Without operation.
yeah, we have another one. I know Econet have left. They've been changing. I think we still have Airtel.
Airtel is there.
And then there's the last one.
Nine Mobile.
Nine Mobile.
Yes. Nine Mobile.
Nine Mobile. Okay. Nine Mobile. Yeah. So those are the five. So it means that each of them have 5 megahertz. So now, out of these 5 megahertz, the channel size or spacing is 200 kilohertz. So we can get about 5,000. How many? Is it up to 5,000 here? If you take, that's 5,000,000,000. That's meg, right?
That's 5,000 kilohertz.
So that's 5,000 kilohertz, yeah. Divided by 200 kilohertz. So how many of 200 kilohertz can we get from here? That's about 25, right?
Okay.
Yeah. So this is what they can, this is what a particular cell we can assign to a particular cell. That's why we now have automatic radio frequency numbers. Automatic radio frequency number. So that each of this frequency is assigned to a number. Say 1, 2, 3, 4. Then you now see that if we have in this place, like in this particular cell, XYZ base stations, now the frequencies assigned here, because they are limited, we now have to be reassigned somewhere in another channel. That's why we do frequency reuse. Okay? So that's why in planning the telecom network, we now have to reuse the same set of frequencies. And we reuse the same set of frequencies considering interference and all of that, okay? Because we cannot use the same set of frequencies in the same channel, in the same cell. That's why it's cellular, because there will be co-channel interference. Now, when we now deal with different frequencies, we begin to deal with adjacent frequency frequency interference and all of that. Now, what does this do? The impact on all of these things, the effect of this is to increase the level of interference in the system on the physical side. But this also can degrade your signal, because should I transmit after all of the signal processing, we have now what we deal with in the electronic side of the process is noise, right? Not interference. Because there's a big difference between noise and interference, isn't it? Hello, are you still with me? Hello?
Yes, we are with you, sir. We are with you, sir.
Now, there's a big difference between noise and interference. So now we deal with noise on the circuitry side. We may not have control over it, white noise, short noise, and all of those. Now, the distortion of the signal relative to that, we cope with that. That's why we have filter designs and all of that on the circuitry side. We use some either active or passive circuit elements to design some filters to resolve some of those problems. At least at some point, if we see that the signal is being attenuated, where we want to find a way to amplify the signal, right?
Yes.
So we use some active devices like your amplifiers. We want to amplify the signal in the signal processing dimension. But once that is done, this signal comes through, we already made mention of that. We deal with all of those digital analysis and all of that, zeros and ones, blah, blah, coding and all of those things. Your particular algorithm, you know, runs on all of those electronic boxes you see in your mobile switching room, right? Okay. Now, but along the line, this signal goes through some very beautiful coaxial cables to this antenna. And then we said that, well, we have to do some modulation because your zeros and ones cannot be transmitted over physical medium, isn't it? Since it cannot be transmitted over the physical medium, we now have to figure out a way to ensure it is analog, right? So if it becomes analog, then it means we can relate with it in terms of voltage variation, right? And then we begin to see something like a signal on the spectrum. So by the time we now convert your, what's it called now? Your zeros and ones, we now have to, your zeros and ones sequence, which we get from coding, now have to be modulated, right? For us to be able to get a carrier. Now, it is that carrier that we can now process as the analog equivalent. And once we do that, we can transmit over this coaxial cable and it gets to this antenna, boom, it goes all out. Now, as that signal goes all out, it begins to interface with other parameters, okay? So at this point, we are no more dealing with signals because once it is induced, you recall all of those, your Faraday's laws. Let's just come to Maxwell, right? Maxwell gave the relationship between the electric and the magnetic field, isn't it? Isn't it? So don't forget, what we still have in this analog signal that we have processed as from the digital perspective, it's still the same, it contains the same information. But once it hits this process, and now it has become voltage variation, there is the level of induction. So from there, we're able to get the magnetic field, such that the signal is now contained in the electric field of the EM wave, right? So the electric field component, we have the electric field component and the magnetic field component. So the signal information is contained in the electric field component. And now, once this is done, that level of induction now gives us what we call your transverse electromagnetic wave, right? Such that the electric field, the magnetic field, and the plane of the direction are perpendicular to each other. And then the polarization has to be aligned with respect to the electric field, isn't it? Because the position of the electric field tells the plane of polarization. We are more interested in the electric component, the electric field component of your EM wave. I'm sure you know why. Hello? Are you with me?
Yes, sir.
I don't know the reason for that.
Okay. Now, what is the voltage equivalent of your electric and magnetic field properties, parameters? You recall your EM wave, right? Well, this is not an EM wave class, but let's just talk to it a little. Do you recall your EM wave class, your EM wave Maxwell equations, right? Do you still recall
Not perfect.
that?
Not perfectly.
Okay, there's no problem about that. Now, we have the circuit equivalent and the field equivalent. I don't want to wipe the board yet. I still have certain things I want to mention here. Okay. Now, the field equivalent deals with your electric field and the magnetic field, right?
Okay.
Now, the circuit equivalent deals with your current and voltage.
Okay.
Okay. Now, the circuit parameter equivalent of your electric field in the field parameters is your voltage.
Okay.
Right? And now,
okay,
what contains the information between current and voltage?
The resistance?
No. I want to transmit. I want to digitize. So this is a digital analog component now. right?
Okay.
This digital component, your continuous, this is a continuous wave, right?
Yes.
Now, if I should put this on a scale with respect to time, what value is this? Some voltage value, right? Maybe 3.5
Yes.
volts, right?
Okay. Okay.
So it means that my information is contained in this pulse, isn't it?
Okay. Yes.
And now the information contained in this pulse, don't forget, we've been processing, right? We've been processing, isn't it? So whatsoever we may have processed, we are saying that, well, we look at the spectrum, this is what we now see, some variations. And what variation, what are we varying here? Are we varying current or voltage with respect to time?
The voltage.
Exactly. So it means that in all of these, that we are looking for the analog equivalent and all of that of my signal based on the fact that we now have to modulate my bit sequence with a modulation scheme so as to have a carrier that we can transmit through a physical medium like a coaxial cable, is that we want that information to be equivalent to some voltage values. And we know that we can now say this is 1, this is 0, this is 1. So in transmitting my 101, it is some 3.5 voltage variation with respect to 0. Okay? And now we say this is a return to 0 coding scheme. It could be a non-return to 0 whereby my 0 comes down to the negative. Isn't it? Well, I don't want to bore you with that. That's not our problem now. But once this voltage now hits my coaxial cable, remember, this is my coaxial cable. This voltage hits this. So what's voltage? Your voltage is more like pressure, right?
Yes.
You have a tap or you have a pipe, okay? So I want to pass water through this. If I should increase the pressure at this point and relative to this point, water will flow, right?
Yes.
So the flowing water is like your current.
Yeah.
But what is driving your current? That is the voltage. That's why voltage is the reference value. That's why now when you now talk about power, power can be appropriately or correctly designated as VI, not IV. You know why?
Yes.
Because voltage is the reference value.
Yes.
Right? Okay. So if I should say power is IV, I'm wrong somehow, technically, but I'm correct numerically. If I should plug in the values, I'm correct, right? But if I should now take it as a vector quantity, I'm wrong because voltage should be the reference value. Well, that's, by the way, let's leave all of those jargons. So the point now is this: the information I'm driving in the analog plane is some voltage value that describes it.
Okay.
And now going by Faraday, once we induce a wire with some voltage and current flows, there's a magnetic field that builds around it.
Yes.
Exactly. Once an electromagnetic field builds around it, then we now have the electric field and the magnetic field components that are perpendicular to each other.
Yes.
Now, once that drives it to the antenna setup, the thing that comes out of the antenna component is the electric and the magnetic field. But we know that the electric field component is the equivalent of the voltage in the circuit analysis or in the circuit equivalent of this process. There are mathematics to that. We'll begin to pull out all of those integral E dot the L is equal to V, right?
Yes.
V is the same thing as integral E to the L, right? You recall?
Okay.
Yeah. So, but that's not our point now. We are not doing electromagnetic, but your information theory and coding relates to all of these things. So I just wanted to see the practical perspective to this. We are going to be doing too much of statistics, it's abstract, but this is the practical equivalent. Now, if my electric field is directly proportional, equivalent to my voltage. So in other words, I can say, looking from the circuit perspective, the electric field, what I see for the electric field is voltage, right? So if I should look from the field perspective, what I see is not voltage, but the electric field component, isn't it?
Yes, the magnetic field.
It's the electric field, not the magnetic field. It's not
Okay,
H.
okay, okay.
I don't see H.
Elec-
This E. I don't see H.
Okay. Okay.
If I want to see H, then I have to talk to current.
Okay.
Right? That's why this is voltmeter related. This is ampere meter related, right?
Okay.
Your magnetic field is ampere related to your meters, right? While your electric field is volts, the unit of measure, right? You recall?
Yes.
It's volt,
Yes.
it's voltage related, isn't it? So it means that your electric field component of the electromagnetic wave of your EM wave contains the same information that have been coming from your zeros and ones, which we can relate with your voltage. So by the time we now have the E field and the H field as perpendicular components moving in this free space, moving in this chaotic channel, we know that that information is still contained in the electric field component. Do you get the idea now?
Yeah. Exactly, exactly.
So when we're now talking about plane of polarization, how you should align your antenna for reception of this signal. If I should have horizontal polarization, so it means that my antenna is horizontally placed. So the E field is going to come out in that horizontal manner. So the receiver, the antenna that will receive that signal must also be horizontal. Must also be horizontally polarized or vertical. But in practice, we are not dealing with that. We are either dealing with circular polarization or elliptical polarization, where we have to deal with both the vertical and the horizontal plane of polarization put together in case in case it tilts in space. Okay, in case the orientation changes, let's put that's the right word, the orientation. So if the orientation should change in space and my expected E field, which is supposed to be horizontal, now goes vertical, I will still be able to trap it with my elliptical or circularly polarized designed antenna. Do you get it? That's why you see most of your waveguides, they are designed as horizontal or as circular or elliptically polarized. Now, you get that, right?
Yes.
Now, this signal now goes off in space. It's analog, okay? And now, as it's going off in space, let's change this color so that we begin to see something different here. Now, it's going off, okay? Off this antenna is going off. Then another signal is also going off. Now, if there's a signal of equivalent power, they could interfere and cancel out or add up. Interference. So that could either lead to attenuation of the signal, probably a signal that is coming off with this strength may not reduce eventually, okay? At some point, we may lose it completely. Now, at times, you see that you just hold up your phone, it's heating up, right?
Yes.
It's heating up because it's actually receiving signal with higher power. These are interfered signals coming into your mobile phone. It begins to heat up, it begins to heat up. Then it heats up to a point, it begins to malfunction depending on the age of your phone. You try to touch it, the screen is shaking. You say, my phone is malfunctioning, right? Now, at that instant, signals could be distorted. Now, should there be distortion of signal, know that, fine, this has become an electromagnetic wave. It hits this antenna, it's trapped. Soon, we convert again to voltage level that drives this cable. And now on this cable, we get into our processing devices, your switches and all, then we are able to extract our zeros and ones again. So as the signal came up this way, at some point it amplified, at some point it was attenuated. Some of those activities may have distorted the position of this signal. So at the point of reconstructing the signal, we may not receive some of these signals in error. So when it now reconverts to zeros and ones. So now let's wipe the board. Let's clear this, clear all. Now, this is a signal we transmitted in this manner. So at the end of the day, from our transmitter, right? So
Yes.
now just look at the entire process we just talked about. That's the physical process in real life, looking at your mobile network. Then now, we now got to the end, to the receiver. And now what I now have is something like this. So I expect this signal to now go through my signal processing system where I have my decoding technique, the decoding algorithm. Now, the decoding algorithm already knows the coding scheme or the encoding scheme, okay? So it knows the encoding scheme, the algorithm. So it's going to use that algorithm to interpret this signal, okay? Now, how will it map this signal with this one? They don't look alike anymore. So if we don't have a proper coding technique, we will receive this entire signal, which is analog, that will soon be converted to a digital or bit sequence. Let's say this was 10110. So at the end of the day, we may not receive 00101. But this does not tell what we transmitted, okay? So, and that is why they now say, well, the only way we'll be able to develop efficient codes, because we are not talking about source coding now. This is not source coding. Because what actually corrects for these errors is channel coding, okay? So we're going to talk about them separately. We'll talk about some source coding strategies and some channel coding strategies, okay? We'll now talk about block codes, convolution codes. So now, for us to have an efficient code that will be able to correct for these errors, we must add some number of redundant bits, okay?
Okay.
In a measured, in a measurable format. And the level at which we add these redundant bits is what gives rise to either a block code or a convolution code. Okay, and now we are going to tell the difference. Shortly, you see that block codes are memoryless codes, and we can use combinational circuits to design them. Okay, you know combinational circuits, isn't it? Your normal AND gates and all of that. But your convolutional codes, they have memory. So since they have memory, in the practical, in terms of practical implementation, we can use sequential logic to design them. And you know examples of some of your sequential logic devices, your flip-flops, right? So with your flip-flops, we can design convolutional codes in practical terms. Okay, what I want you to do in this course is that I want you to, in as much as we are going to be dealing with abstract parameters, I want you to also, at every point in time, try to relate it with its practical implementation, okay? So everything you've learned so far, real life. So everything you've learned so far in the electrical electronics engineering field begins and ends in information theory, okay? So this is the home of the of communication or electronics, as it were, information theory and coding. So everything rises and falls on information theory and coding as far as the communication and the electronics field is concerned. Okay. Now, now we want to recover this. And for us to do that, I said we need to add some number of redundant bits. So let's assume, for instance, let me just give you a simple analogy. Let's assume I want to transmit just a single bit, okay? And then I try to add some redundant bits, 1, okay? So should I transmit this, for instance, and then I receive 101, my receiver can easily detect that something is wrong. This can be easily corrected. It can tell, well, if it's just one bit error, if my code can detect 1 bit in error, it can tell that 111 was transmitted. But we'll run into a problem if I should receive 001, it's going to decode this wrongly and say it's 000 that was transmitted. Do you get that?
Yes.
Because
there are two errors already.
yeah, now why? Because we have added redundant bits. The actual bit that we need here, the message bit, is 1. And we added, so the more redundant bits we add, the better the coding technique. Do you understand? So if you want to improve, if you want to increase the efficiency of the code, increase the number of redundancy. Once you increase the level of redundancy, the capacity of that code to be able to correct error will be high, but there's a trade-off. You waste bandwidth.
Exactly what I wanted to say.
Yeah.
Because it is going to be expensive. You have to look at the bandwidth
exactly
to transmit all that.
Exactly. So the bandwidth is one problem. The transmission power is another problem. Okay, because now let's assume I'm going to transmit this with 1 watt, 1 bit. Let's assume I was transmitting only 1 bit. I'm going to transmit 1 watt. Now, if I want to transmit this 3, so it's going to be 1/3, right?
Yes.
1/3. So I'm going to be transmitting at lower power. And this also, if we now look at the signal to noise ratio parameter, then it may become very difficult to reconstruct this signal because the power has dropped, right? So at that, and that now may cause some recovery problem and power issues. So this may lead to loss of signal as well. So you now see that for the communication expert, there are a whole lot you now have to put into consideration when you want to design optimal codes. Okay, because increasing the redundancy will increase the capacity or efficiency of the coding scheme, but do you have that bandwidth, the cost, the power implication, okay, and the complexity? So you now see that there's a trade-off between complexity, there's a trade-off between cost, and a whole lot of factors. Well, we'll try to consider some of those things as we progress in this. Well, this is just an introduction in this course. So, well, before we call it a day, or better to take some questions. So we now see that one important thing in terms of designing error control coding is to add redundancy, isn't it?
Exactly.
Yeah.
Exactly.
So it means that to combat errors over the communication channel, which I already mentioned, we can deal with 2 schemes. The automatic repeat request, forward error correction. I mentioned that earlier. Automatic repeat request requires retransmission, and forward error correction does not require retransmission. But those are 2 broad categories. But now, if we now look at this error control coding relative to adding redundant bits to the message bit, because here, this is our message bit, right? And this is these 2 are redundant bits.
Redundancies.
Now, so based on the level of redundancy, errors are corrected, by the receiver or at the receiver by decoding. It's here we correct errors. It's at this point. So at the transmitting point, we add redundant bits, right? That's at the point of encoding. We are encoding here.
Okay.
Right? So we add redundant bits. So here,
decoding.
We are decoding, sorry. So here we are decoding, okay? Okay. So it's at this point of decoding we correct errors, isn't it?
Okay.
Yes, that's where we correct errors, because we already know what we have transmitted from the transmitter. So we know over the channel, both based on circuitry problems, based on electronic, we have a lot to deal with. So at the electronic device level, we deal with noise, right? And you must have dealt with that in your electronics study, where you talk about your short noise, your white noise, and all of those, right? Now,
Okay.
outside that, at the pure air interface or interface level, let's look at the interface level, where we now have to deal with how, when the signal is taken from the voltage level through Faraday's law, we now have the electromagnetic equivalent, and the signal goes through space in a multi-part channel, interference problem comes in. And now we now begin to deal with fading issues, right? Large scale fading, small scale fading. We begin to deal with that. That now impacts on the signal. And this multi-part itself causes one major problem, intersymbol interference, right? It's a big problem with multi-parts, right? That's one thing we deal with. And that's why we now have to move from a single carrier, let's just, to combat this anyway, to combat this, we now move from single, oh my goodness, single carrier to multi-carrier schemes, right? Multi-carrier modulation schemes. So instead of talking about all of those, your BPSK, which are single carrier, BPSK, quadrature phase shifting, quadrature phase shifting, quadrature amplitude modulation, those are single carrier. We now begin to talk about OFDM, orthogonal frequency division multiplexing. We even now have normal and all of those, but normal, where those are access technology. I'm talking about the modulation. So if we now want to talk about the access technology for OFDM, we now say OFDME, right? Okay. Isn't it? Yeah. Mm-hmm. That's the access, but we're talking about the modulation at this point, you know, the orthogonal frequency division. So that's multi-carrier. Now, what are we trying to deal with? We are trying to deal with intersymbol interference. Okay? Now,
Okay.
well, yeah, that's what we're trying to deal with, because the impact of your multi-part problem, you know, we made mention of the actual channel, right? It's chaotic. So the signal bounces off here, this bounces off here. So another signal falls off from the ground and all of that. It hits this part, then there's signal scattering. So you see a single signal hit the floor. Then we now have multiple signals going off due to signal scattering, reflection, and all of those things. Diffraction, so many things happening all together. So this channel becomes chaotic. So we now have multiple components of that same signal. So at some point, multiple components of a particular signal having the same frequency and all of that now interfere again. They could cancel out. They could even amplify, combine. So that alone, we now distort the exact signal coming into, so it causes intersymbol interference. At the end of the day, when we're supposed to be receiving 10110, we are receiving 00101. So now we have made mention of, okay, fine, we want to correct this. Let's add redundant bits. So based on how redundancy is added, there are two major categories of code. That's where I'm going to, okay? Because we're going to be looking at these codes. Two major categories of code based on how redundancy is added. So the first is block codes.
Okay.
And the second is convolutional codes. We are going to talk about them in detail, okay? Convolutional codes. So I already mentioned that here the codes are block by block basis, okay? And if they are block by block basis, now instead of transmitting 101, so this becomes a block of code just like that. So now they are block by block basis. The impact of a particular block on a previous block is not there because it's memoryless. So this is memoryless, just this memoryless. And then if it's memoryless, we know we can achieve this using, I already mentioned it, combinational logic, okay? Simple to design. So our block codes, should we say, well, try to design a simple block code? You should be able to, now we'll look at some of those block codes. Now, we also have convolutional codes. Now, they have memory because they use shift registers, okay? So in other words, what we get in this shift register, let's say 2, is dependent on what was fed into shift register 1. Okay, so it has memory. So if it has memory, it means that we can achieve this using sequential logic, right?
Okay.
Now, know that all codes are designed based on how redundancy is added. Okay?
Okay.
And now that we have the message bit that needs to be transmitted, let's wipe this. We have the message bit that is to be transmitted. So message bit, say 101, that's the message bit, right? Message bit.
Okay.
So if we should add redundant bits, say 111, for instance, I'm not talking about any type of either parity, or we are not talking about all of those things yet, either even or odd or whatsoever. We are not talking about all of those yet, okay? Because your redundant bit, just take note, your redundant, well, I'll still talk about this in detail, I'm just introducing. Now, your redundant bits are also called parity check bits, or better still, parity bits, okay? So when you see these, just know that we are actually talking about the same thing, okay?
Okay.
Redundant bits, parity check bits, or parity. But when we get to syndrome decoding, we use parity check bits for syndrome decoding to detect and correct some errors, okay? So that's the essence for redundant bits. We want to correct errors at the receiver. So we need to add more bits. But the way we add these redundant bits is what determines the type of code. And we have so many. We have turbo codes and all of those that we use in telecom. But that's fine. But the broad categories, we have block codes, we have convolutional codes. Now, another class based on this, we have systematic codes. Let's wipe this. We have systematic codes and non-systematic codes. Now, we'll try to analyze the non-systematic codes from systematic codes. Now, in systematic codes, you see that the message bits, it's a message bits, then we have redundant bits. Redundant bits. So in a systematic code, the redundant bits is explicitly added to the message bit. They are not mixed up together. Okay? So we can, there's a clear distinction between the message bit and the redundant bit. So that's why in most of the coding, the codes that we'll play with, the systematic codes are preferred. Okay? Because there is this explicit distinction between the message bit and the redundant bit. Do you get that? So this, as it is called a systematic code. This is a systematic code. Okay? So for a non-systematic code, for non-systematic codes, you can tell that the redundant bits are implicitly embedded in it. So it's all mixed up. Okay, we cannot give a clear distinction between the message and the redundant bits in a non-systematic code.
All right.
I don't know if that's clear.
I understand.
So going forward, we are going to be playing with more of systematic codes. We'll play with like Rich Solomon codes. They can correct bus codes, okay, bus errors, okay, and the likes of Hamming codes and all of those, just one bit in error and all of that. We'll talk about them. Then we'll also talk about convolutional codes. You know, we'll talk about those ones. Then we'll talk about maximum likelihood decoding scheme, the likes of beta-B decoding, you know, how interesting they are, how they're able to correct multiple bits in error and all of that. So I think this is just a summary overview of what we are going to be talking about in information theory and coding. I'm so sorry I've taken so much time. let's say in our next class, we'll try to begin with the information measure. We'll begin to talk about what information really is, because that's where we can begin to take things from, you know. Just like I said earlier, information is simple. It's just the measure of uncertainty, okay, with something that we want to transmit, okay? So that's where probability comes in, okay? So that there you now see that information is the same as log to the base of whatsoever we want to use as a system of measurement. If it's base 2, that's bits, okay? So if we don't want to use base 2, let's say we use base E, the measure of information will be nat, that's natural logarithm. And if we use, let's say, base 10, that will be Hartley or Ban, okay? It will be Hartley or Ban, okay? So, but we are used to bits, just zeros and ones, okay? So now, how do we measure this? I'll stop here anyway. This is not what we want to talk about today. So if, for instance, my probability, the probability here is 1. So the probability of 1 will give us what? 0, isn't it?
Yes.
Let's say it's equal to log 1 over 1 base 2. The log of 1 is 0. So it means that if we are certain about the information, there's no information passed. If I know what you want to tell me, you have not passed any information. So, but isn't it? Have you given me any problem? Yeah. So those are the interesting things we are going to be looking at now. So you now see that information as it is the measure of uncertainty. Information is the measure of uncertainty with a transmitted message. So if the probability should increase, okay, so if it's highly probabilistic, then information is passed. Okay, so so the more uncertain, the more the information. So if the degree of uncertainty is 0, then it means that the probability of occurrence is certain, is 1. So there's no information passed. So from there, we'll now begin to relate with the transmission. So we'll begin with the meaning of information. Then when we now transmit it, what happens? That's what now happens within the channel. So at the receiver, we are now designing systems because we are not certain what is coming. Do you get the point?
Yes.
Yeah. So we are not certain what is coming. So we now begin to deal with that. And by the time we now begin to deal with the mutual information relative to what is transmitted and received, then we now deal with it in terms of the probability. Then we cannot tell at what point can we use this to design the capacity or the maximum rate of the channel. Then in practical terms, theoretically, we talk about data rate, right? But when we now talk about the practical system, the actual amount that is actually transmitted after the design, we now say throughput, right? So those things we'll deal with them much later. But hope we have been able to give a general overview of what information theory and coding entails. So any question, please?
Well, sir, I must say that I enjoyed the lecture today. It's so exposing. But sir, I want to ask, is it possible for us to have the lecture material so we can read along with you?
Yes, you already have the lecture materials. I already made some videos in last class. You can just watch them ahead and we are good to go.
I have those ones. I mean, text, something like a note that we can read along.
And those are the textbooks I recommended in the outline I sent to the forum.
Okay.
Yeah, those are really interesting materials. So let's see if we could share them again. If we could share. Okay. I'm sure you can see this. Yeah. So these are that's the content. So we already made mention of some of these details. Okay, so blah, 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 the objective learning outcome, the content. So, well, the first thing I put up here is, well, I'll say my lecture notes have been made into videos, right? And that's what
Okay.
you have in the YouTube link. So if we click on this, so let's see, if I click on this, will it open? Can you see it? Is it opening?
Yes, it's opening.
Yeah, so these are the things you see in that channel. So so these are all the notes there, right? So so this is the first Shannon information measure. So it's about 1 hour plus. Then after that, you want to go to the second. So this channel information, okay, then you go to the second asymptotic propagation property and entropy rate. Then data compression, you take that is the third one. Then the fourth one, channel capacity. Then the fifth one is block codes. Then the sixth is convolution code. So we're going to update this. Rate distortion is not here and some other topics, you know. I think we had those ones in class, but there was no time to make the video, and that was it. So I pray time to make the videos. Okay.
It's interesting.
Yeah, so you could look through these notes before the class, and then outside that, there are other, let's go back to this, yeah. So we have Thomas M. Kober. It's an interesting book, okay? Very interesting book. We have Robert J. McEllis. We have Roberto Togneri. Then we also have David J.C. McKay, Information Theory, Interference, and Learning Algorithms. Interesting books. Interesting books. So you could pick up these books, you know, and all of that. The beautiful thing is information theory left to me, just like the Maxwell's equations is the foundation of our study. Information theory is the foundation of electronics and communication engineering. You know, so with it, you are able to, you know, relate with everything that has to do with the communication system from a pure statistical perspective, you know. And these books will guide you, will give you all the information you need, at least to, you know, to begin with. So any other question, please?
No, sir, I don't have another question, except others do.
Okay. So any other question before we call it a day? Okay, so in the absence of none, I think we'll call it a day and hope to see you in the next class. We arrange that. And nice meeting with everyone. Just like I said earlier, I will assume we've covered the entire topics in the course. Or just like one of my professors once said, if the curriculum have been mentioned, then it means the entire course have been covered. Now that you have all the topics and you equally have all the lecture notes online, so we can begin to walk through exercises. And if you are prepared for the exam tomorrow, let me know. We'll get it done.
Thank you so much, sir.
Okay, do have a great day and see you in our next class.
Good night, sir.
Yeah, good night.